Welcome to A Listen at a Time, where we will be learning something, a listen at a time. Today, we're diving into the global semiconductor manufacturing and supply chain. You've likely seen the headlines, chip shortages, geopolitics, all that. But today, we're really digging deeper, trying to understand how this whole industry actually works, globally speaking. We've got a pretty detailed breakdown here, the processes, who the main players are, and how all these different countries kind of depend on each other. Our mission really is just to give you a clearer picture of this super complex, super important global landscape.
Exactly. I mean, semiconductors, they're basically the foundation of everything tech,
Right.
right? And making them it's a truly global effort. We'll be sort of tracing that journey, from the raw stuff right through to the finished chip and looking at the specialized roles different places play and the big strategic forces that are kind of shaping where it's all headed.
Okay, so let's kick off with the basics.
Yeah.
How do you actually make a semiconductor? It sounds incredibly complicated.
Oh, it is. It really is. But you can basically break it down into two main stages, right? First, there's the front end. That's all about making the silicon wafers and then building the super intricate circuits onto them. Think of that as the really high precision manufacturing part.
Okay, front end, wafers and circuit.
And then second, you got the back end, usually called ATP assembly, test, and packaging. And that's where those finished wafers get turned into individual chips that actually work and can be put into our phones or computers.
And both stages need just mind-blowing accuracy. Yeah, like way beyond your typical factory floor stuff.
Absolutely. We're talking features measured in nanometers,
Yeah.
a billionth of a meter.
Yeah.
It's hard to even picture. Someone once said, a nanometer is to a meter what a marble is to the earth. Just, tiny. And that level of precision, that's exactly why the front end especially needs these ultra clean rooms. Even a tiny speck of dust can just ruin everything.
Right, the bunny suits and everything. So, okay, the wafers. Where do they start? You mentioned silicon.
It starts with silicon, which is super common, comes from sand mostly. But the key thing is purifying it. You need electronic grade polysilicon. That means it's got to be like 99.999999% pure. Just insanely pure.
Okay, purify the silicon.
And you take that pure stuff and use this really cool process. It's called the Czochralski method or CZ method. Basically, you melt the polysilicon, then you dip in a tiny, perfect crystal, the seed crystal. You slowly pull the seed up while rotating it, and this huge, perfect, single crystal cylinder of silicon grows underneath it. It's called a boule.
A boule, like a loaf of bread.
Kind of looks like it, yeah. A big gray crystal loaf. These things are big, too, usually 300 millimeters across, like a big pizza. And they're even looking at 450 millimeters now.
Oh, and while it's growing, they add tiny, tiny amounts of other elements of dopants to control exactly how it conducts electricity later. It's all planned.
Huh. That controlled growth sounds absolutely critical. So you've got this giant silicon boule. Then what? Then, you slice it, like incredibly thin slices. These are your wafers. But they're not ready yet. They go through grinding, etching to get the thickness just right. And then this really important step called CMP, chemical mechanical polishing. It uses chemicals and polishing pads to make the wafer surface incredibly smooth, like almost perfectly flat, mirror smooth, essential for what comes next.
Okay, super smooth silicon discs. Now for the actual circuits. How do they build those, layer by tiny layer?
Right. This is where the complexity just explodes. This is wafer fab, the front end. It's basically a cycle you repeat hundreds of times. You add thin layers of materials, you remove parts of them, you pattern them, and you tweak their electrical properties. The main steps are deposition, putting materials down.
Like spraying paint, but way more precise.
Sort of, yeah. Techniques like CVD, PVD, ALD. Different ways to deposit atoms, basically. Then there's removal, mostly etching.
Carving away the bits you don't want.
Exactly. And patterning, which is the key bit, photolithography, using light to draw the circuit patterns. And finally, doping, changing the conductivity in specific spots. Hundreds of steps.
Photolithography, that sounds like the real bottleneck for making things smaller and smaller.
It absolutely is. It's like super high-tech stenciling or photography. You coat the wafer with this light-sensitive stuff, photoresist. Then you shine light, UV light, or for the really cutting-edge stuff, EUV, extreme ultraviolet, through a mask. The mask has the pattern for one layer of the chip. Where the light hits or doesn't hit, the resist changes, and you can wash away the exposed or unexposed parts.
Leaving the pattern behind on the wafer.
Precisely. And that pattern guides the etching process for that layer. Then you clean it all off and start the whole cycle again for the next layer.
Deposition, light patterning, etching, doping, repeat hundreds of times.
Yep. Building these incredibly complex 3D structures, almost atom by atom. And there are different ways to do each step, wet etching with chemicals, dry etching with plasmas, rye, DI are for really fine control. ion implantation for doping.
And, crucially, you keep using that CMP polishing between layers to keep the surface perfectly flat as you build up. Otherwise, it'd get lumpy and wouldn't work.
Then strip off the leftover photoresist, and you're ready for the next round.
Wow, the sheer number of steps. No wonder it's so specialized and expensive. Okay, so circuits are built on the wafer. Now what? Back-end time.
Exactly. Now we move to the back end, ATP, assembly, test, packaging. This is where we go from that whole wafer covered in identical circuits to individual working chips that are protected and ready to be soldered onto a circuit board. It's kind of bridging the gap, from the nanoscale chip world to the macro world of electronics we actually use.
Okay, so how do you get from that wafer to the chips that end up in, say, my phone?
First up is wafer test. Tiny probes touch down on each little square chip called a die on the wafer. They run electrical tests to see which ones work and which ones are duds. Mark the bad ones.
Find the failures early. Smart.
Yep. Then the wafer might get thinned down from the back, depending on what the chip's for. After that, die singulation. Basically, they use a very precise saw to cut the wafer up into all those individual dies.
Okay, so now you have a pile of tiny silicon squares.
Right. Then comes die attach. You take each good die and stick it onto a substrate that's like a little base that provides support and electrical connections. Then you connect the tiny contact points on the die to the contact points on the substrate. Traditionally, that was wire bonding super thin gold wires. But for high-performance chips now, they use flip chip, where the die is flipped over and connected using tiny solder bumps. Much shorter paths, better speed.
Faster connections. Makes sense.
Then encapsulation. The fragile die and its connections get encased in protective plastic or ceramic, that black casing you usually see. That's molding. After that, final test. Rigorous testing of the packaged chip to make sure it works under real-world conditions. Functional tests, power tests, maybe even burn-in testing. Finally, they mark it with logos and part numbers, put it on tape or in trays, and ship it off, ready to go into a product.
That whole journey, it's incredible. And you mentioned the global aspect. That brings us right to the supply chain itself. You said it's intricate, interdependent.
Oh, incredibly so. It's super complex, costs a fortune to set up, capital intensive, and it changes fast. Plus, everyone depends on everyone else. You can sort of break the chain into stages. R&D, obviously. Then design, that includes the software tools, the EDA, and the core designs, the IP. Then manufacturing, that's the foundries making the chips or the IDMs doing it all. Then the ATP or OSAT guys doing the back-end stuff we just talked about. And finally, distribution and getting it into your phone or call. And generally speaking, the highest value parts. That's the design and the really advanced leading-edge manufacturing.
And we hear all these acronyms flying around: IDM, fabless, foundry, OSAT. Can you just quickly recap what those business models are?
Sure. So IDM, integrated device manufacturer. Think Intel, historically, or TI. They design and manufacture their own chips. Do it all in-house, mostly. Fabless companies, like Nvidia, Qualcomm, AMD. They design amazing chips, but they don't have their own factories, their own fabs. They outsource the making part.
Okay, so they focus just on the design.
Right. And they send those designs to foundries, like TSMC, the giant in Taiwan, or Samsung's foundry business, Global Foundries, SMIC in China. Their whole business is manufacturing chips for other people. And finally, OSATs, outsourced assembly and test. Companies like ASE or Amkor, they specialize just in that back-end part, packaging and testing the chips made by the foundries or IDMs.
So the industry kind of broke apart from everyone doing everything?
Yeah, that's a big trend. The old IDM model got disaggregated. The fabless foundry model really took off. It lets companies specialize, which is great for innovation, right? Nvidia focuses on GPUs. TSMC focuses on being the best maker. But it also creates these really complex webs of dependency and potential weak spots, vulnerabilities.
And it's not just who does what, but where they do it, right? That geographic specialization seems key.
Absolutely key. The geography is super specialized. The U.S. still very strong in chip design, all the big fabless names, the crucial EDA software, IP. And a lot of the super complex manufacturing equipment comes from U.S. companies, too. The CHIP PS Act is trying to bring more actual manufacturing back, though.
Okay, U.S. for design and equipment.
Europe. Well, the Netherlands specifically has ASML. They're the only company making those critical EUV lithography machines for leading-edge chips. Huge bottleneck, huge advantage. Europe also has strengths in chips for cars, industrial stuff. Germany, Netherlands again. Plus R&D, special chemicals.
And Japan, I hear they're crucial for materials.
Totally crucial. Japan dominates in supplying the really high-purity silicon wafers, Shinetsu, SOL. And essential chemicals, photoresist, special gases, plus some important equipment makers like Tokyo Electron, TLL.
Okay, so the raw materials and some gear. Taiwan.
Taiwan is the giant of contract manufacturing. TSMC is king, especially for those advanced, cutting-edge nodes. UMC is big and more mature stuff, plus big OSATs like AS and fabless like MediaTek, just central.
Right, TSMC is the name everyone knows. South Korea.
South Korea is memory central. Samsung and SK Hynix dominate DRAM and NAND flash memory. Plus, Samsung has the world's second biggest foundry business, competing with TSMC at the high end. And strong OSATs, too.
Memory and number 2 foundry. What about China?
China's role is complex and changing fast. They're the biggest consumer of chips by far. They're rapidly building up manufacturing capacity, but mostly in what's called mature nodes. Older, but still essential chip tech. Salem like Huahong are big there. They're also huge in the back end, OSAT. Dominant, actually, in assembly and testing, including advanced packaging now. JCET is a major player, growing fast in chip design too. But critically, they rely heavily on foreign tech for the really advanced leading-edge chips and the machines to make them.
Okay, consumer, mature nodes, back-end leader. And Southeast Asia.
Yeah, places like Malaysia, Vietnam, the Philippines play a really significant role in that back-end ATP stage. Lots of assembly and testing happens there.
So if you could trace one single advanced chip, it really could touch almost all these places.
Easily. Imagine a new AI chip, right? Designed by Nvidia in the U.S.
Okay.
Using EDA software from Cadence or Synopsys, also U.S. Maybe using core tech licensed from ARM in the U.K.
Right.
Then the design file goes to TSMC in Taiwan. They make it using machines from ASML in the Netherlands, Applied Materials in the U.S., TLL in Japan.
Right.
On silicon wafers from Japan.
Wow.
Once the wafer's done in Taiwan, maybe it goes to Malaysia for advanced packaging by an OSAT company. Then that packaged chip goes into a server assembled in, say, China or Mexico, which then gets sold globally. It just shows how tangled it all is and why things like trade tensions or, earthquakes in Taiwan make everyone nervous. These are real choke points, driving all this talk about making supply chains more resilient, diversifying.
Yeah, that paints a really clear picture, so interconnected.
Yeah.
Okay, looking forward then. What are the big tech frontiers? Where's the innovation happening?
Well, the push is always, always for smaller, faster, more power-efficient chips. That's the drumbeat of the industry, which brings us to these process nodes. You hear about 3 nanometer, 2 nanometer. What do those even mean now?
Yeah, I was going to ask. It's not really the size of a specific thing anymore, is it? It feels more like a generation label.
Exactly. You nailed it. Historically, it kind of related to like the gate length on a transistor, but now not really. It's more a marketing term, a shorthand for a new generation of tech that packs in more transistors, performs better, uses less power compared to the last one. Right now, the top companies, TSMC, Samsung, Intel, are making or ramping up 3 nanometer chips, using slightly different tech under the hood, actually. The next big jump is to 2 nanometer class stuff. That's probably coming around 2025. And that involves some pretty major changes in how the transistors themselves are built.
Right, the transistors. We went from flat ones to FinFETs, and now the buzz is all about GAAFETs. What's the difference and why the change?
Okay, yeah, this is fundamental. It's the shape of the switch, basically. Old transistors were flat, 2D. Then came FinFETs, field effect transistors. Think of the channel the electricity flows through as a vertical fin. The gate, which controls the flow, wraps around 3 sides of that fin. Much better control than flat. Standard for years, down to 5 millimeter, even 3 millimeters for some.
Better control, less leakage.
Exactly. But to go even smaller, you need even more control. Enter GAAFET gate all-around FET. Here, the gate completely surrounds the channel on all 4 sides. Imagine tiny little nanowires or flat nanosheets carrying the current, with the gate wrapped all the way around them. This gives you like the ultimate electrostatic control. Less leakage current again, better performance for the size, better power efficiency. It's seen as essential for getting below 3 nanometers.
So everyone's moving to GAAFET for the next nodes.
Pretty much. Samsung actually started using their version called MBC FET, which uses nanosheets at 3 nanometer bare. Intel's calling theirs Ribbon FET, also nanosheet-based, coming at their 20A and 18A nodes. And TSMC is expected to make the switch to GAAFET at their 2 nanometer node. So yeah, the key idea is moving from 3-sided gate control with FinFET to 4-sided control with GAAFET. It's a big architectural shift.
A big shift needed to keep Moore's Law or something like it alive. Okay, so new transistor shapes. But how do you actually make these impossibly tiny things? That brings us back to lithography and EUV, right?
Absolutely critical. Lithography dictates the smallest pattern you can print. For years, we used DUV, deep ultraviolet light. but its wavelength is relatively long, like 193 nanometers. To print features much smaller than that, like below 7 nanometer, they had to use really complex tricks, multi-patterning. Basically, print, etch, print again, etch again.
Oh, what?
Very complicated. Adds cost, lowers yield.
So EUV was the breakthrough.
It's exactly. EUV extreme ultraviolet has a super short wavelength, just 13.5 nanometers. That lets you print much finer features in a single exposure. It simplifies making 7 millimeter, 5 millimeter, 3 nanometer chips enormously. Became essential. But the machines, they're monsters. Made only by ASML in the Netherlands. Incredibly complex, cost maybe $200 million each or more now.
$200 million for one machine. Wow. And ASML is the only supplier.
Yep. Total monopoly on commercial EUV, which, has
Yeah.
huge geopolitical implications with export controls and everything, and they're not stopping there. Next up is high-NA EUV. NA is numerical aperture, basically better focusing, higher resolution again, needed for 2 millimeters or below, expected to start being used around 2025, 2026. So yeah, lithography tech, especially EUV access, is a massive enabler, but also a massive choke point.
It sounds like just shrinking transistors further is getting incredibly hard and expensive. Is that why we're hearing so much about advanced packaging, like finding other ways to boost performance?
Precisely. That's the whole more than more idea. If you can't just cram more transistors onto one chip easily, maybe you can connect multiple chips together more cleverly. Advanced packaging is all about that. How do you integrate different chips, maybe made on different processes, into one package effectively? So you get things like 2.5D packaging. Imagine putting different chiplets, little specialized chips, side by side on a base layer, an interposer, with super fast connections between them. Often used to put high bandwidth memory, HBM, next to a processor.
Okay, side by side. And 3D is stacking them.
Yep. 3D packaging stacks dies vertically. Connect them with tiny vertical wires called TSVs through silicon vias. This gives you even higher density, shorter connections, lower power. Again, HBM is often stacked 3D style. And this whole idea of chiplets is huge now. Break down a big complex chip, so skin into smaller functional blocks. Make each chiplet on the best, most cost-effective process for its job, maybe some parts on 5 millimeters, some on older nodes. Then stitch them together in the package using 2.5D or 3D. Gives you better yields, more flexibility, potentially lower cost.
So you mix and match the best bits. And HBM itself is a kind of advanced packaging.
Yeah, high bandwidth memory is a perfect example. It's stacks of DRAM memory chips connected vertically with TSVs, all put right next to the processor using 2.5D integration. Gives you massive memory bandwidth, crucial for AI and supercomputing. And there are even newer techniques coming, like hybrid bonding, create copper-to-copper connections between stacked chips, even denser connections. It's really blurring the lines between the front-end wafer making and the back-end packaging. Foundries, IDMs, they're all investing heavily in this now.
Fascinating. And one last tech frontier, it's not just silicon anymore, right? We hear about silicon carbide, gallium nitride. What's their role?
That's a great point. Silicon is amazing, but it has limits. Especially for high power, high frequency, high temperature stuff. That's where wide bandgap or WBT semiconductors come in, like silicon carbide SiSiCac and gallium nitride GaN. They can handle higher voltages, higher temperature, switch faster in some cases. So silicon, it's becoming huge for power electronics in electric cars, the inverters, chargers. Also in solar power, industrial motors, handles high power well. GaN. Also great for power, especially high frequency. Think those tiny, super fast phone chargers, that's often GaN. Also really good for RF, radio frequency stuff, like in 5G base stations.
So specialized materials for specific tough jobs where silicon struggles.
Exactly. And people are even researching crazy stuff like 2D materials, just atoms thick, that could maybe lead to bendy electronics or real super tiny sensors. That's still more research lab stuff. But yeah, using these new materials, silicon, GaN, it adds another layer of complexity to the supply chain, different materials, different factories.
It really is an incredibly complex global puzzle.
Okay, let's shift focus a bit to one of the biggest pieces of that puzzle right now, China. We know there's a massive push there for self-sufficiency in semiconductors.
Yeah.
Can you give us the overview of that strategy? What's driving it?
Yeah, China's drive for semiconductor self-sufficiency. It's a huge deal. It's a long-term, state-driven strategic priority. What's behind it? Several things, really. Fundamentally, they want to reduce their dependence on foreign tech, especially from the U.S. There are economic reasons, building their own powerful industry, supply chain security reasons, making sure they have access to critical chips, and frankly, national security reasons. We saw policies like Made in China 2025 signal this ambition years ago. Maybe the specific targets weren't hit, but the direction was clear. Then there's the big fund, this massive government investment vehicle, pouring billions and billions into building up the domestic industry, manufacturing, equipment, materials, design, across the board. Phase 3 just got announced, another huge chunk of money.
So serious government backing, massive. And then later on top of that, you have the geopolitical tensions and especially the U.S. export controls that started ramping up in 2019 and got really tight in 2022, 2023. These rules restricted China's access to the most advanced chips, the EV machines needed to make them, certain design software, even U.S. engineers supporting Chinese fabs. This was widely seen in China as a deliberate chip chokehold, and it just massively cranked up the urgency for them to build their own capabilities. So the goal now is really building a resilient, homegrown supply chain. Pragmatically, they started by focusing hard on the more mature technologies where they could make faster progress.
Okay, so huge ambition, massive investment, and now real pressure from restrictions. Where does China actually stand today? How close are they to that self-sufficiency goal?
Well, despite all the effort and investment, overall self-sufficiency is still pretty low. Estimates are usually around like 12 to maybe 14% of their own needs being met by domestic production. But that number doesn't tell the whole story. They've made huge strides in specific areas. Mature node manufacturing is one. They're building fabs like crazy for older generation chips, 28 millimeters above. Projections show they could have like over a quarter of the world's capacity for these kinds of chips soon. They're also really strong, maybe even world-leading now, in OSAT, that back-end assembly and test. And they're getting quite good at advanced packaging, too. Domestic equipment makers are growing fast in certain segments, etching tools, cleaning tools, and chip design is booming, especially for specific applications, and they're really pushing RISC-V, that open-source alternative.
Okay, so strengths in mature manufacturing, back-end, some equipment, design. But what about the weaknesses? Where's the dependency?
The big dependencies are still there, especially at the cutting edge. Leading-edge logic chips making the fastest processors like those below 7 millimeters. They just can't do that at scale without EUV machines, which they can't buy. That's the biggest hurdle. Advanced manufacturing equipment in general, they still rely heavily on imports from ASML, Applied Materials, Lam Research, TL, KLA. Domestic tools are catching up in some areas, but lag overall, especially for the highest specs. EDA software, tools for designing chips, still dominated by U.S. firms, Synopsys, Cadence, and Siemens EDA, core IP like processor designs, still heavily reliant on ARM from the UK, and critical materials, the Curis silicon wafers, advanced photoresists, often still sourced from Japan, Europe, or the U.S. So it looks like a pragmatic strategy. Try to dominate the huge market for mature chips while pushing the limits of what they can do domestically for more advanced stuff, even if it's harder or more expensive.
Oh, right. We heard about SMIC, the big Chinese foundry, actually making 7-nanometer chips for Huawei phones, despite not having EUV. How did they manage that?
Yeah, that caused a stir. SimSip basically pushed existing DUV lithography to its absolute limits. They used very complex multi-patterning techniques, likely something called SADP, self-aligned double patterning, maybe even SAQP for 5-millimeter attempts. It involves using multiple DUV exposure and etch steps for a single layer, effectively drawing finer lines than one DUV pass could manage. It's how the industry made chips like 10 millimeters and early 7 millimeter before EUV became widespread. So they used this approach to make chips like the Kirin 9000S for Huawei.
So it's possible, but is it practical or competitive?
That's the billion-dollar question. It's definitely possible, and it shows incredible engineering skill. But it's way more complex than using EUV. It requires many more steps, which increases the chance of defects, lowering the yield, the percentage of good chips per wafer. It's also slower, lower throughput, and significantly more expensive. Estimates suggest making 5 millimeter this way could cost 40–50% more than TSMC using EUV. So is it sustainable for high-volume, mass-market, leading-edge chips? Probably not competitive long-term without some major breakthroughs. But for strategic needs, for specific domestic products, maybe in lower volumes, yeah, if they've shown they can do it, it's a workaround, born out of necessity.
It's a very complex workaround. So building that whole ecosystem,
Yeah.
equipment, materials, design tools, that's the real long game for self-sufficiency. What are they doing there?
Absolutely. It's a massive, multi-pronged effort. On equipment localization, companies like Narrow Technology and AME are growing really fast, making good progress in etching tools, some deposition tools, cleaning. They're gaining share within China. But for lithography, the key bottleneck, SME is the main domestic player, and they're still focused on DUV for mature nodes like 28 millimeters and older, way behind ASML, especially on EUV, which they just don't have. Overall, domestic equipment share is still low, maybe 15% or so, but rising in specific niches.
Okay, equipment is progressing, but litho is the big gap. Materials.
Similar story. Lots of investment in domestic production of silicon wafers, photoresist chemicals, to companies like AMEC and CHC. But achieving the extreme purity and consistency needed for the most advanced chips, that's really, really hard. Still reliance on imports for the top-end stuff. China does have leverage with some raw materials, though, like gallium and germanium, and has used export controls there.
Right, and Ito software and IP, the design side.
Still a major dependency on Synopsys, Cadence, Siemens EDA, and ARM. Domestic EDA alternatives are emerging, but they're still nascent, not really competitive at the high end yet. Which is partly why China is pushing RICV so hard. It's an open-source instruction set architecture, a potential alternative to ARM, UK, Japan owned, and by 86, US owned. Lots of government backing. Big companies like Alibaba's T-Head, Huawei investing heavily, focuses often on IoT, edge devices, AI accelerators, maybe a long-term play to build a parallel ecosystem around it.
Well,
But high-performance RICV still lags ARM and by 86 significantly.
interesting. And you mentioned advanced packaging earlier. China's strong there.
Yeah, that's a real area of focus and progress. OSATs like JCET are already doing sophisticated 2.5D packaging, supplying international customers, even with chips made elsewhere on advanced nodes. Tongfu Microelectronics, TFME, is working with AMD on chiplet packaging, developing HBM tech with domestic memory makers. They see advanced packaging integrating multiple chiplets effectively as a way to boost system performance, even if the individual chips are made on slightly older nodes, kind of compensating for the lithography gap. So lots of investment there. It really is a comprehensive strategy, trying to plug gaps across the entire value chain to reduce those foreign dependencies.
So putting it all together, what does this relentless drive by China for self-sufficiency mean for the rest of the world, for this whole global industry? It's undeniably reshaping things. China's huge build-out in mature node capacity. That could really change the global supply and pricing for those types of chips, the ones in cars, appliances, industrial gear, potentially leading to oversupply or price wars down the line. Their progress in advanced packaging, their push into RISCV, these show they're finding ways to innovate around the restrictions, not just trying to replicate the West's path exactly. And these restrictions themselves, they're not just slowing China at the very edge, they're forcing this unique innovation path. Like the DUV multi-patterning, it's tough. But it also drives creative engineering. Building this parallel domestic ecosystem, even if it lags in key areas now, over the long term, could it lead to a kind of split? A bifurcated tech world with different regions using somewhat different underlying technologies or standards? That's a real possibility. So it's not just about competition, but potentially about divergence, too.
Could be. This whole deep dive really underscores, I think, just how much is going on under the surface. It's tech, it's economics, it's geopolitics, all wrapped up together. And for you listening, understanding these forces, the tech shifts, the supply chain geography, China's strategy, the impact of controls, it's becoming pretty crucial to make sense of where technology and maybe even the global economy is heading.
Okay, here's where it gets really interesting then. A final thought. If this trend keeps going, this focus on regionalizing supply chains, maybe even nationalizing them to some extent, what does that do to the pace of innovation globally? Does it slow things down? Does it make electronics more expensive for everyone in the long run? Something to chew on. Thanks for taking this listen with us.